All right, guys, it's time for fun with math. And so today we are back to talk about what? We're going to talk about series here. So series, and then we will talk about something called the divergence test. So again, let's go back just to kind of review what is a series. So by a series, what do we mean? So we mean a series, I usually use a symbol S to represent a series. So S is equal to the sum n equals 1, and we talk about infinite series in this class. So from 1 to infinity of a sub n, which is really a short way to write a sub 1 plus a sub 2 plus a sub 3. And these are all just some numbers, basically, plus dot, dot, dot. And so it goes on forever and ever. And we've seen lots of different types of series now, I guess. So we've seen what geometric series and a telescoping series. And then we talked a little bit about those P series. And so what we're going to do today is we're actually going to give a definition for convergence. And so to understand the definition of convergence for a series, we need to look at what are called the partial sums. So if you give me a series S here, its partial sums, we write S sub k. And make that k better. So S sub k right there. And so S sub k is equal to what? Well, it's the partial sum. So it's the sum from n equals 1, but instead of going to infinity, we just go to k and of a sub n. And so really, this is a shorthand way to write a sub 1 plus a sub 2 plus, and then we write dot, 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 but at the end here, we write plus a sub k. And so this is called the kth partial sum. All right, and for a series to converge, right, so we say S converges if what? If the S sub k's converge. So what does that mean? So i.e., that is to say, the limit as k goes to infinity of the S sub k exists. And it diverges otherwise. And so S then diverges if the S sub k's, and as a sequence now, diverges. So this kind of gets us in to why we have to study basically sequences before we study series. So we have sequences and we have series. So remember, sequence is just a list of numbers, whereas a series is a sum. So we do sequences first because in order to define a series converging, we have to turn it into a sequence. And so here's our series right here, and we turn it into a sequence by looking at the partial sums. And so if the partial sums converge, then we can conclude that the series actually converges. So let's take a look at some examples here, and we'll kind of use this definition to kind of help us determine if things converge or diverge. But a little bit of warning, it's really hard to use the definition to show something converges or diverges. And so that's why we'll have a bunch of tests that kind of help us. So what we're going to do here basically is we want to find the first 5 partial sums, just to kind of practice finding partial sums of each of these series. And then we'll give an argument based on these sums as to whether the series converges or diverges. And so here are the 3 series we're going to do. So A, B, and C. And we're just going to do these one at a time. So let's take a look at this first series here. And so this is our series S. So I'm going to give it a name. And let's just look at the first 5 partial sums. So we have S sub 1, which is just basically the first term of this infinite series. So you just plug in 1, so you get 1 over 1 plus 1, which equals 1/2. And then S sub 2, which is going to equal basically S sub 1, then plus the next term. So you're going to have 1/2 plus, and then the next term is when you plug in 2, right? So you start this at 1, so you plug in 1, then you add when you plug in 2. So when you plug in 2, you get 2 divided by, and then 2 plus 1 is 3. And then you can add these together if you want to on a calculator to see what you get and math frac it. I'm just going to tell you what you guys get. Well, here, let me show you, I guess. I mean, I think you guys are all probably familiar with math frac, but if you're not, I'll show you real fast here. So it's pretty simple to do here. So you have 1 divided by 2, and then plus 2 divided by 3, spits out a number, and then you can math frac it if you want to get the actual number here. So you need to show your work, but then you can use your calculator if you want to kind of give you this number. And sometimes it's nice to give the decimal form of these too. So this was like 0.5, because at the end, remember, we have to create an argument to see what these are actually equal to see if this thing actually converges or not. And so this one was 1.16 repeating. So over here, where are you at? There you are. So 1.16. And for repeating, guys, you just put a bar over the top of it. And then S sub 3, well, it's S sub 2, so it's like 1/2 plus 2/3. And then plus the next one, you're going to plug in 3 now, and so you get 3/4. And you can kind of see a pattern starting to emerge here. And my 4 looks pretty bad here, so let me fix it. And so that's going to be equal to, and again, you can use your calculator, and you can just add, actually just add 3/4 to the last thing we had. And it's until it's this number. Again, you can math frac it, right? Because here you get 23/12. So sometimes I'm looking for a pattern here. I don't really see a pattern, but I like to write down the number here. So 23 over 12. And so what's that equal to? And so here, that was 1.91662. So I'll put equal to 1.916 repeating. So equal to 1.916, and then that's repeating here. And then we keep on going on these things here. So what's next is I add what? So S sub 4 is equal to then plug in 1, right? Plug in 2, plug in 3, and then plug in 4. And so we'll just add 4/5. So 4 divided by 5. And so what is that equal to? So let's check this one out. And so now I have what? I can just add basically 4/5 to this thing. And I get this 2.716 blah, blah repeating, which again, I can math frac that. And I get out this number right here, right? So this is equal to 163/60, which is equal to really, as a decimal, 2.716 repeating. And finally, one more, S sub 5, which equals 1/2 plus 2/3 plus 3/4. And just keep going. There's a nice pattern here, so you don't even have to look at the formula anymore. Then plus, and that's 5/6. And so that's equal to, so just to make sure we didn't make any mistakes on adding all these up, let's just do this real quick. So 1 divided by 2, plus 2 divided by 3, plus 3 divided by 4, plus 4 divided by 5. All right, I should get that last answer. Yep, I do. And then plus 5/6, that's the last one. Just checking to make sure I didn't make any mistakes. And I get this 3.55, which if I math frac it, it gives me 71/20. All right, so I have this 71/20 here, which is really equal to, and so you can kind of see what the actual number is, that 3.55 again. So 3.55. All right, so we found the first 5 partial sums. So just kind of practicing what a partial sum actually is. Now comes actually the hard part. And so you'll see these are relatively tricky. You really have to kind of get in there and dig. It's like we want to create some sort of argument based on these sums as to whether these converge or diverge. So just looking at the numbers, looking at the decimal forms, you can kind of see they keep getting bigger. So you got 1, 1.9, basically 2.7 something, 3.5. So it looks like they just, keep getting larger. So if I had to give you a guess, it looks like this is going to go to infinity to me. So as a guess, I would say, S diverges. And you might say by inspection. All right, so I'm just looking at it. I'm just thinking, I'm feeling like it's going to diverge by inspection. If you want to give a better argument, right? Just by inspection, is like just by looking at it, which is not a very good argument. Just like I feel like it's going to happen. But if you want to give a better argument, you can kind of see what's happening here. So if you take a look at these sums here, so notice if you take 1/2 plus 2/3, that is going to be bigger than 1. And then here you have that 1/2 and 2/3 again, so that's going to be bigger than 1, then plus something else. But then S sub 4, that fourth partial sum, that's going to be bigger than 1. And then when you take 3/4 and 4/5, that's going to be bigger one. That's where the 2 is really coming from. So notice these ones here, that's kind of where they're coming from. And then down here, you get it again, bigger than 1, bigger than 1. So when you add them together, you get something bigger than 2. And then notice it's 3 because you get the remainder stuff kind of adds up to even more. If you did one more of these, so just for fun, if you did one more of these, you'll see you can actually create an argument here. So you have 1/2 plus 2/3, and that's why I wrote these out, because if you don't write them out, it's hard to see the argument you might make. So 3/4 plus 4/5, and then you have plus 5/6, and then plus 6/7. And then notice I put parentheses around these because each of these terms, when you add them together, these two terms add them together, you get something bigger than 1. So that's going to be bigger than 3. I don't know what the number is, but I know it's bigger than 3. So what I just created here was an argument to show that what? That right here, whatever number that is, it's going to be bigger than half of that number. Basically, what I can tell you guys now is that if you have this S sub k, it's always going to be bigger, not bigger than k, but bigger than k over 2. And why do I know that? Well, this is certainly true because it's 1 plus 1 plus 1. S sub 4 is good. S sub 2 is good. And then let's put greater than or equal to. Because if you do the ones in between here, notice each of the remainder terms here is bigger than or equal to 1/2. And so it's always going to be bigger than whatever this number is right here, and then divided by 2. So that will always work. So because of this, I can say the limit as k goes to infinity of S sub k, it's going to be bigger than or equal to the limit as k goes to infinity of what? Well, k over 2. And then we know what happens when you plug in infinity here. You get infinity over 2, which equals infinity. Therefore, I can say S diverges. Now, this is an argument that uses the definition. So S diverges by definition. And that's a pretty strong argument you can give. All right, now I am using a little bit of my, inspective skills, I guess. I don't know if that's actually a word, but I am using a bit of inspection here to kind of look at this and say, oh, look, each one of those two terms in collected error is bigger than 1. But it's a pretty solid argument, I think. All right, let's move on to the next one. And so here, what do we have? So we have this sum right here. So this is my S now. And so I want to do the first partial sum, so S sub 1. And so what's the idea? Now, on this one, you have to be a little bit careful because you're actually plugging in 0 first. So instead of calling it S sub 1, I might call it S sub 0. It depends on what you want to do. Like if you want to do the 0 sum or the first or whatever, I'm going to do S sub 0 because it just starts at 0. And so that's -1 to the 0, which is equal to 1. And then I'll do S sub 1, which will be equal to, now I do 0 and 1, and I add them together when I plug it in. So I get basically -1 to the 0, and then plus -1 to the 1. And so that's my first partial sum. And so what is that going to be equal to? That's going to be equal to 1, and then -1, which equals 0. And then I'm going to do S sub 2, which is going to equal what? Well, it's the first sum before, so -1 to the 0, plus -1 to the 1, and then plus -1 to the 2. And so what's that equal to? Well, you get 1 minus 1 plus 1, which equals 1 again. And you just keep on going, and you kind of see what's going to happen. It's going to go 1, 0, 1, 0, and forever, basically. Let's just keep writing it out. So S sub 3 is equal to, and that would be -1 to the 0, plus -1 to the 1, and then plus -1 squared, and then plus -1 cubed, which again is going to equal, you have 1 minus 1 plus 1 minus 1. It's going to equal 0. And I do it again. So S sub 4 is going to equal. Now here, I'm getting a little tired. So I'm just going to write out 1 minus 1 plus 1 minus 1 plus 1. I'll show a little bit of work so you can see what we're thinking. And I get back 1. And finally, the fifth partial sum, S sub 5, you get 1 minus 1 plus 1 minus 1 plus 1 and minus 1. And so that's equal to 0 again. All right, so things to kind of notice here, you're basically just kind of jumping around between 1 and 0. So you get 1, 0, 1, 0, 1, and 0. And so if you want, we could just actually from that, we can conclude. So S diverges. And now here, instead of saying just by inspection, I might try to give a little bit of an argument because let's give an argument. So it alternates between, this one's easier to write up, between 1 and 0. So there's a nice, sort of argument you could give. In fact, we could go back to this first one here and probably do a better argument. So S diverges by inspection, and we could say because it looks like it is getting, I guess I should say it looks like, because it looks like the partial sums are getting, so I should say that. So let's see, because we could get confused with the series, because it looks like the partial sums are getting bigger. So it looks like the partial sums, so partial sums are getting bigger. Bigger. There we go. All right, so we get a better explanation there if we want. All right, so back here, we can say S diverges because it alternates between 1 and 0. That's a fine argument, I think, just based on the partial sums. Now, if you want to use the definition, how would we do that? Well, we'd have to say something like, notice that S sub 2k, so what happens when it's even? Well, notice you always get out the number 1. So S sub 2k is always equal to 1. Whereas S of sub 2k, if you want plus 1, it can be plus 1 or minus 1. It really doesn't matter. Is equal to, well, notice they're always 0. So when you're odd, you always get out 0. So the limit as n goes to infinity as S sub k equals to, it does not exist because why? Because the limit as k goes to infinity of S sub 2k, so that the even partial sums is equal to 1, and the limit as k goes to infinity of S sub 2k plus 1, so those are the odd partial sums, and so that's going to be equal to 0. So basically, the limit is not the same, right? So if you go to infinity, no matter, there's a fancy way to say, so whatever sort of subsequence of the index you take there, it should always converge to the same number. So since, the even partial sums go to 1 and the odd partial sums go to 0, they're just not the same, and so that limit does not exist. So we can say, therefore, S diverges by definition. All right. Now, again, using the definition is really hard. So, if you just wrote something like this, S diverges because it alternates between 1 and 0. And because, again, maybe I should have wrote here, because instead of it, maybe we should have written because the partial sums, right? Because the partial sums alternate. So let's just leave out the S. So the partial sums alternate between 1 and 0. So maybe it's better to write it like that. All right. So that's the big idea. And again, hopefully you're like, yeah, it's kind of tricky. Using the definition and creating arguments, it's very tricky to do. Again, that's why we're going to have tests that help us to do this. All right. One last problem. All right. So Again, we want to find the first 5 partial sums of this guy right here. So here's our series. And they start us off at 1, so we'll just do S sub 1, which is nice. And so now you just plug in 1 and you get -1 squared over 2, which is equal to 1/2. And then S sub 2, it's going to equal, well, it's going to be the one before, so we'll just write 1/2. And then plus, and now we'll plug in 2. And so now we get -1 cubed over 2, which equals what? 1, ooh, did I plug in 2? Did I plug in 1? I made a mistake above, guys. I got to fix that. All right, shouldn't get the same number out. So let me fix this right here. So this I need to delete. This I need to delete. This I need to delete. All right, so this is -1 squared over 1, and which is equal to 1. And so now down here, I just have a 1. And now I plug in 2, and I get -1 cubed. Now I'm good. Okay, so now we're good. And so what do I have here? I have basically just 1, and then minus 1 over 2, which equals 1/2, which is equal to 0.5. So it's nice to know those decimal representations of these fractions. And then we do it again. So I get S sub 3. And again, I'm not going to write out this. I'm just going to use this stuff here, which is kind of nice. So I'm going to do 1 minus 1/2, and then I'm going to plug in 3. So plus, brain's not working. So minus 1/2, and then plus, and then I come up here and I plug in 3 now. And so I get -1, and then 3 plus 1 is 4, and that's over 3. And so that's going to be equal to 1 minus 1/2 plus a third. Oh, I kind of see the pattern starting to merge here. Now I'll use a calculator to find out what that is. And so on my calculator, I have 1 minus 1/2, or 1 minus 1/2, so 1 divided by 2, and then plus 1 divided by 3. It's going to return a number. I can math frac it if I want to quickly get sort of fraction form here. And so what does that equal to? That's 5/6, which then is equal to, on my calculator, 0.83 repeating. So let's check that real fast, make sure I didn't make a silly mistake. Yep, so we're good. And then we do the next one. So S sub 4 is equal to, and now I see the pattern emerging right here. So I don't have to really go back up here if I don't want to. So what can I do? I just write 1 minus 1/2 plus 1/3, and then minus 1/4. And so that's going to be equal to, and again, on my calculator, I can just take off 1/4 from the last one. And so there's that sum. I can math frac it if I wanted this fraction form. And again, I do that because sometimes a pattern will emerge, but not always. But it's nice to see what the fraction form is. And then also the decimal representation. So 0.583 repeating. So down here, all right, 0.58 and then 3 with a bar above it. And I'll do one more here. So S sub 5 is equal to, and so what is that? That's 1 minus 1/2 plus 1/3 minus 1/4. And so when we change signs like this, we say the series is alternating because it goes plus minus, or minus plus, or plus minus plus minus, and then it'll go plus 1/5. And so that's going to be equal to, so finally on my calculator, I'm going to add a 5th to this guy right there. It gives me that number. I'll math frac it again, and I get this little answer here. So 47 over 60. And so right here, I'll write 47 over 60, which is equal to, and again, the calculator tells me what the decimal form is, so 0.783 repeating. So I'll write here 0.783 repeating. Okay, looks good. Looks good. All right, so I have the 5 partial sums, the first 5 partial sums. I see what their sums are, so it goes 1, 0.5, so it goes up, it goes down, it goes back up again, it goes back down again, it goes back up again. So what's going to happen, I see, it's kind of going to go up and down, kind of like we did before, right? So before it went like 1, 1 and 0, 1 and 0, 1 and 0, but there's a small difference, and that little difference actually forces the series to converge. So it goes up and down, but it doesn't go as up as much, and it never goes as down as much. So it's kind of like up, down, up, down, up, down, up, but smaller and smaller each time. So it starts to actually level off kind of and head towards a number. So to show you that, the easiest way to do this is just to draw a number line. So let me draw a number line here, and then just check this out. So I'm going to start at 1. All right, so this is my S sub 1. Right, and it has distance 1. And maybe let's flip that. So let's put the number down here and S sub 1 up here. And then S sub 2, I go back to 0.5. So here, let's just move it over and put 0.5 here. And so here's S sub 2. And then S sub 3 right here, what happens to it? It goes up, but not quite as far as 1. So it goes up right about here to 0.83. And so that's my S sub 3. And then what happens here for S sub 4? Let me change colors. So S sub 4 is this guy right here. So it doesn't fall all the way down to 0.5, just a little bit above it. So right here at 0.583. Oh, and this is repeating, I guess. So I should put a repeater on there. And then this is my S sub 4. And then finally, my S sub 5 right here. So notice it doesn't quite make it to this 0.83, just a little bit below it. So 0.783 repeating, and that's my S sub 5. And so what's happening is what? So basically, I'm starting here, and I bounce down to S sub 2. I bounce back up, but not quite as far as F sub 1, so there's S sub 3. Then I bounce back down here to S sub 4, but not quite past S sub 2, and I bounce back up to S sub 5. And so I'm going to keep on bouncing, and there's some number. I don't know what it is, guys, but there's some number here that it's going to bounce around. And it just bounces back and forth, but it gets ever closer to that number because it never passes the partial sum before it, basically, on either side. So it's kind of like bouncing around and getting closer until you can't even see it oscillate anymore because it's so close to that actual number it converges to. So here, I would conclude that this picture basically implies that my S converges, and we can give it a little reason because the partial sums are bouncing. This is not a mathematical term, guys. This is just something we're writing. Right? It's an argument, right? So are bouncing around some number. And getting closer to it. Because it's possible to bounce around and not get closer to, and getting closer to it. All right, and so that's sort of the argument that I would probably give. Now this one, it's super hard to use, or it's much harder to use the definition. So we're not going to even try. So this one's just kind of like, hey, look, it seems to be bouncing around some number, and getting closer to it. So our argument is that. We drew a little picture, so you can kind of see that argument in play. And again, the definition's really hard to apply, and that's why we have a bunch of tests that we're going to learn that'll help us to do it. It's kind of like, like with the definition, you guys remember the definition of the derivative? It's like you don't want to use a definition of the derivative. You don't have to, and that's why we make all the derivative rules so we can avoid the definition and just use the rules. It makes the problem a lot simpler to solve. All right, so we have one last thing I want to talk about here, and that's what? I want to talk about this divergence test. So the divergence test is one of our favorite tests to use to test if a series does what? And hopefully you're saying it only tests if a series diverges. So this is only a test for what? And you say divergence. So very important. This will never be a test for convergence. It's only going to test if the series diverges. And if the test doesn't work, it tells you nothing. Right? So if you can't apply the test, it's like, well, if it may converge, it may still diverge, right? But if this is true, so if you have your series here, S, right? So there's my little series. If the limit as n goes to infinity of the sort of terms in your series does not equal 0, right? So not equal to 0, then we can conclude that S diverges. So let me say this again. If you take the limit as n goes to infinity, right, of the terms of your series, so these are the a sub n's, right, so the a sub n's right here, if they do not equal 0, then we can conclude S diverges. Although, right, so be careful, if the limit as n goes to infinity of a sub n is equal to 0, oh, that's awful infinity. If it's equal to 0, what can you include? Nothing. Nothing, people. We can conclude nothing, all right? So really important that we kind of point that out. If those terms of your series, right, go to 0, we just don't know anything about the sum. It could converge, it could diverge. But we do know if they're not equal to 0 as you go to infinity, then we can say it diverges. So let me show you how this test works. It's super easy to do. Again, it's one of our favorite tests to use because it does tell us a lot of series do diverge. All right, so what do we do first? So here's our first series. I'm going to identify my a sub n. So a sub n is equal to n. And so I'm going to take the limit as n goes to infinity of n. And of course, that's equal to what? Infinity. So which is not equal to 0. So therefore, my series S, so let's give it a name. So S equals. So my series S diverges by the divergence test. So right, divergence test. Let's do it again. Super easy, right? Let's do it again. So here's our next series. Let me change colors here. So here's our next series. Oh, I haven't used purple. And so what's our a sub n? So a sub n is just the terms of our series. So a sub n is equal to n over n plus 2. And so we run a limit on it. So limit as n goes to infinity of n over n plus 2. Well, we know what that's equal to. We can cancel off the lower degree term if you want, and that's equal to the limit as n goes to infinity of n over n. So the n's cancel, so that's equal to the limit as n goes to infinity of 1, which equals 1. And honestly, guys, if you just concluded, you took this and said it's equal to 1, I'm fine. But you have to write not equal to 0. And then we write therefore what? My S, right? Let's use purple again. So my S, this is my series S, diverges, and we have to write this, diverges by what? By the divergence test. Perfect. Okay, so there's our conclusion. So in these problems, you always have to kind of run the test. I always try to identify, what I'm using, but you have to run the test. You have to make the assumption, right? The assumption, if it's not equal to 0, then you can conclude, right, that it diverges basically, but you have to show this, right? That's not equal to 0, it's not equal to 0, and then you can make your conclusion, therefore it diverges. All right, one last one. So let's do this one in blue here. So sine of n, so my a sub n is equal to the sine of n, and so now we take the limit as n goes to infinity of sine of n. And if you want, you can just plug in infinity to see what you get. So sine of infinity, and then you can just think about that. So what happens with sine of infinity? It just goes up and down always, right? Always up and down. So it never settles down on a number. It never gets closer to a number, right? So it's just going up and down between -1 and +1. And so that means that this limit does not exist. So it does not exist. So it cannot equal 0, right? So that's sort of like our premise. I think I said assumption before. I meant premise. That's the premise of the divergence test. And then the conclusion is, so if it satisfies the premise there, we say, therefore, S diverges by the divergence. I'm using a different pad today, guys, to write, so it's a little rough. So divergence test. And notice on all of these, this is not a test for convergence. This is a test for divergence. So we conclude with diverges. If we have a series, so check this out. If our series looks like this, n equals 1 to infinity of 1 over n, check it out, right? Your a sub n is equal to 1 over n, and then the limit as n goes to infinity of 1 over n, that's also equal to 0 because it's 1 over infinity. So that's equal to 0. But what can we conclude by the divergence test? Nothing, right? So very important. You can conclude nothing, right? We have no idea what's going to happen now. It could converge or it could diverge. We don't know what this series S is actually doing. But what's nice, Remember that tough problem we did in the very beginning, because I'm sweating because it's taking so long. But way back here, that was a really hard argument we made down here. So way down here, we made this argument. That was kind of a tough argument to create. Now, we don't have to make that argument anymore, because why? Here's our a sub n's. Our a sub n's are just n over n plus 1. So all I have to do now is take the limit as n goes to infinity. So I just take these terms, and you can see I get out 1, which is not equal to 0. So therefore, and this is not an argument per se. I mean, this is like a conclusive fact, right? If you run this test, boom, we know it's going to diverge if it's not equal to 0. So therefore, this series diverges by the divergence test. All right, so super easy to apply. All right, last little thing I want to talk about with you guys is just to give you an argument as to why it works. I don't like to get too deep into these types of things, because then they get you guys get lost in the details. So what I usually do is try to just give you an idea of like, why would a series diverge if it doesn't satisfy this criteria right here, right? So this little premise that the limit as n goes to infinity a sub n is not equal to 0, then we can say automatically S is going to diverge. And the reason for that, and we're just going to take an example, pretend like it was a number that was not equal to 0. So suppose you took a limit as n goes to infinity of a sub n, and suppose it was basically equal to 1. So what does that actually mean? So that means basically you have your series here, which is, the sum n equals 1 to infinity of a sub n. And then what's happening here? And so, you have a sub 1 plus a sub 2 plus a sub 3 plus, and you just keep on going out forever and ever. The fact that this limit is some number that's not 0, what does that mean as you go further out? Basically, what it means is there's at some point in time, your a sub n's are starting to look like 1s. So after some point, who knows where it happens, what's happening is you're basically adding up a bunch of 1s, ... And you're doing that forever and ever and ever. Now, it's not exactly 1, but it's forever close to 1. So 1 plus 1 plus 1, that's why I put it in quotes. It's like 1 plus 1 plus 1. So this thing is going to equal infinity. So when you get it equal to a number, basically it should be obvious. If your terms are going to some number, then when you add up those terms, it's going to blow up to infinity, right? For some positive number. So that's basically the idea. And we're not going to get too more technical than that, because if we get into that definition, we have to involve, the definition of limits. And I don't know if you guys have noticed this, but in calculus, we've avoided really using a definition of limits because there's an epsilon delta definition we shy away from and only use in our more advanced calculus classes called real analysis. All right, that's all I wanted you guys to see there. And so we're done.